Everyone. Today we are going to talk about transport in magnetic metals. Magnetic materials where you have net magnetization and also a larger conductivity, usually the transition metals. So in these materials, not only the charge is going to transport, but also the angular momentum will transport, which is the basis of spintronics. So spin plus electronics. Look to the learning objective. So here we are going to learn how the electronic band structure of magnetic metals is different compared to non-magnetic metals, and how does it affect the transport of charges as well as spins. If we look to the content, we will talk firstly about band structure by taking an example of iron BCC metal, and then we will take a look to one successful story, which is giant magnetoresistance effect. How we can get a band structure. So if we talk about electrons in crystalline systems, here we are talking about metals. They are periodic systems and therefore modeled as periodic arrays of atoms, where electrons are more localized, more or less to the parent atom, and has hoping probability to go to the neighbor. So if you look here, electrons will be localized to this parent atom, but they have non-zero probability to hop here and here. Down the equations of motion of the system in second quantized Hamiltonian formalism. And if you diagonalize this Hamiltonian, then you will get an equation which will tell you what allowed eigenstates, what allowed energies of these valence electrons are as function of momentum. So if you say here is the Hamiltonian and here is the Hoping probability, and there was some potential. So if you diagonalize this Hamiltonian, you're going to get this eigenstate telling you what type of energies a valence electron can get, let's say, as function of momentum. So now if we see dispersion relation, so values of the allowed state as function of energy and momentum, here you can see this dispersion relation. So for the conduction band is usually drawn upward and opposite is for the valence band. If you assume that the size of the system is larger than the interatomic distance, so the length L is much larger than the interatomic distance, in that situation we are talking about reciprocal space, so the change in K, delta K, is going to be really small, and these 2 points will be very closer to each other. So you can, instead of showing this point, you can actually draw a continuous line like this. So you will get a band structure. So here is a band structure and this is the dispersion relation. So band structure is actually a visual representation of allowed quantum states as function of K. So now if we talk about where to put Fermi level, so Fermi level is the energy which the highest electron will get. So if you have a glass of water, you start filling up. Same as you can think of filling up electrons. So where the last electron will go, that will be your Fermi level. If we talk about insulators, there usually you have a gap between conduction band and a valence band, and Fermi level stays in between. However, for transition metal, semi-metals, or very good metals, usually you do not have any gap between the conduction band and the valence band, and this Fermi level will stay in this gapless state. So as we are interested only in metals, so I put my Fermi level here within this gapless state. And let's think about perturbing the system with some characteristic energy scale, the perturbation corresponding to an applied voltage bias, and then the response being the motion of electrons. The fact is that all values at the Fermi level, there's always an infinitesimally close quantum state for electrons to respond with. So you will always have a quantum state where electron can go. So you have states here, state here. So always a state very close to the Fermi level is available. Will have very good conductivity. But now the point here is that the dispersion relation which we have shown here is very simple one. There is only parabolic like dispersion is shown here. However, in reality, when we talk about real material like transition metals, where you have a lot of electrons, a lot of orbitals to consider, so you have to consider d orbitals, p orbitals, as well as s orbitals, and you have to consider the orbital overlap. So the um, band structure is going to look more complicated. And let's consider an example of iron and see how the band structure will look like. Band structure of non-magnetic iron, which is crystallized in a BCC structure. So the electrons can move in a crystal, so the total energy in a crystal is a sum of potential energy, which is of this molecular origin, plus a kinetic energy. So here what we are plotting along this axis here is the wave vector, that is the crystal's momentum, and here is the energy. We put the Fermi level at the zero energy. Now if we look at the x-axis here, gamma point means that electrons have no kinetic energy. So here we can pick one gamma point. So here you have no kinetic energy, but if electrons gain kinetic energy, they will get more and more mobile, more and more speed, and its energy will increase. So you look here it's flat, and then this band has a lot of dispersion, so energy is increasing if you go this direction or this direction. So this is actually S band electrons because they have a lot of dispersion, and S bands are actually the electrons which are very mobile. So you can recognize here at the lower energies you have S band type character. Here is also more S type character. But one important thing is that there is this spaghettis, and the spaghettis have almost no dispersions, and these are your D and F electrons. They almost do not really contribute to the conductivity of material, but one important thing, you can see that they are the spectres are very close to the Fermi level, so they really influence the electron transport, which you have to keep in mind for looking further. So how many states are occupied in a given band? That is a question. That is more easy to calculate if you have an understanding how many states are available in a certain sliver of energy. If you talk about here, how many states are available in this energy sliver, or here, how many states are available there. It would be nice to know the number of states. If I fill up these states according to some temperature, I want to know how many states do I uncover in a certain energy sliver. So I can perform integral along those states more easily, and that is what is called density of states. So in short words, we want to have density of states. So here the density of state is plotted as function of energy. So our Fermi level is here. As we started with non-magnetic BCC iron, you can see that the density of state on your left side as well as on your right side is almost equal and identical. And here, if you want to identify S contribution, S bands are more like this one. So here these are S character, because you can see at lower in energy you have parabolic dispersions if you see your band structure, and the spectres were more close to the Fermi level. So this here this is actually more D-like character, but overall the density of state are plotted for all the electrons sp and d here. I want you to see how the band structure of a ferromagnetic metal looks like. So here is the band structure for ferromagnetic iron, and you can see that the solid line represent the spin up and the dashed line represent the spin down, and there are a lot of bands, but for us the important ones are to pay attention is these spaghetti lines. You can see one important difference, that the spaghetti lines are now splitted. There is dash line which went up the Fermi level, and there is the solid line which moved down the Fermi level. And if you look the density of states, you can really see also here. So spin down electrons move up the Fermi level, and spin up electron move down the Fermi level. And it is because of the Stoner criterion, because when you have a lot of density of states which are d electrons, here a lot of d electrons are there, so there will be a very high Coulomb repulsion, due to which it's more favorable that this band gets split, which is the Stoner criterion. So you will see that when we talk about these transition metals, some of them become ferromagnetic and the bands get split. Main important message here is that now we have different number of density of states available at Fermi level for spin up electrons and spin down electrons, and that is the key point. We can simplify this picture a little bit just by drawing s electron contributions like this with this purple um, shape, and we can draw also the density of states from the d electrons contributing. Just a simple representation is shown here, so you can still track down that the density of states of spin down electrons is distributed in a way that there are some levels available above the Fermi level and some field state below the Fermi level. However, spin up electrons is all the way down to the Fermi level. So now if we look how the electrons in the metal behaves, so here you can see that this yellow are the electrons, and they move in the metal and they get scattered from electrons, and they also get scattered from nucleus. And if the scattering is very large, you will get very low conductivity, and if the scattering is small, you will get high conductivity. And this is a simple 2D model which is crude but works very well for metals. You can see that there is scattering time, and if the scattering time is large, you will get very large conductivity, meaning that the scattering is not so much inside, and you also need larger density of states. Already seen that the s electrons are the one which are actually mobile. They get very large kinetic energies. Their velocities are very large, which is shown here. So s electrons has very large velocities. However, d electrons does not have that large velocities, and they are not so mobile. But one very important point here is that d electrons are not mobile, but they cause scattering. So if you look to the scattering rates, so here scattering time is plotted as an inverse, so it's a scattering rate. So scattering rate for s electrons has a very large contribution from st scattering. It's a well-known concept. So s electrons are getting scattered from d electrons, and if there is large density of state available at the Fermi level from d electrons, which is the situation for spin down electron, the scattering rate will also become very large. Ferromagnetic metal, as we have different density of states for spin up electrons at the Fermi level and spin down electrons at the Fermi levels, which means that we will have different scattering rates. As at the Fermi level, the density of states is not so much available for spin up electrons, so you will have less scattering rate, and for spin down you will have high scattering rate. So one important key point here is that you have spin dependent scattering rate in ferromagnetic metals. It is also shown in this picture. So if an electron is coming, it will have larger mean free path. So the distance between two scattering events is drawn here. It will be much larger for spin up electron. However, as spin down is getting more scattering, this mean free path is going to be different for spin down electron. So you have some spin dependent scattering events. Can also be understood in an equivalent circuit resistor model. So you are sending some current, you will have spin dependent scattering. So spin up electron will have some small resistance compared to spin down electron. Here is high resistance because there is a large density of state of d electron available at the Fermi level. You can think of this that there is a large traffic on the way of spin down electron. However, the road for the spin up electron is quite empty. So in this way, you can think of current density as two channel model. So there is spin up electrons moving in one channel and spin down electron moving in one channel. When they have different current densities, you can define a spin current, which is actually a difference of these two currents. The important thing here is that for spin current, you must remember that it's a flow of angular momentum. So sometime from this reason, people put this h power over 2e just to emphasize that it's a flow of angular momentum. But for simplicity, I will just take this equation to further discuss. This is actually the famous two current model. You can also understand it in this way. So in normal metal, you have equal density of states for spin up and spin down electrons. So total overall, you have actually only charge current which is flowing. So spin current just cancels out. However, if you talk about spin polarized ferromagnetic metal, so if you talk about ferromagnetic metals, you will have spin polarized current. So charge as well as spin is moving. But as the bands are split in ferromagnetic metals, you have different density of states available for spin up and spin down. Let's say you have 2 spin up electrons, 1 spin down electrons. Overall, 3 electrons are moving, but 1 spin is moving. So you have 1 net spin moving in one direction, meaning that you have a total flow of angular momentum. This actually led to the discovery of GMR effect, giant magnetoresistance, in 1988, which was the beginning of actually Spintronics. For the GMR effect in 2007, Albert Fert and Peter Gunsbrook got the Nobel Prize. This was actually a very big achievement. This after the discovery, the devices were on in the market immediately. So in 10 years, you have in your hands devices which work on the effect of GMR effect. The other big success was spin transfer torque. So discovery of spin transfer torque, and their further development is shown in the blue color. So these two were the big successes. There are also other success stories, but I will just cover these two. And this has really changed the way we think about spin currents. I would like to show you what is giant magnetoresistance effect briefly. So we are only talking about one stack configuration, which is current in plane. I will not talk about current perpendicular. And if we look to the stack, it's simply 2 ferromagnetic layers separated by a normal metal. One important thing here is that this normal metal usually is the one which has very weak or almost no spin orbit coupling, because you don't want to have the current spin dependent scattering, so you do not want to lose the spin current. So that's why you want to put something in between which does not really affect your spin current. So now if we look here, there are 2 configurations when you have large fields. This side or this side of the curve, the magnetization is parallel to each other in these 2 layers like this. And when you have a zero field, the magnetization of these 2 layers are perpendicular to each other. So in these 2 configurations, if you measure the resistance of the stack as function of field, you will get a change in the resistance this change was actually the GMR effect, and GMR ratio is actually defined as this change in the resistance divided by this resistance measured at the zero field. So the important thing is that if the change in the resistance is larger, then the larger the GMR effect. If you can remember the previous discussion about the density of state, we can understand this by this GMR effect by the density of state picture. So now you have 2 ferromagnetic metals. I have shown the density of state exactly same way, because as magnetization is in the same direction, the split of the density of state will also be in the same direction. So now you can think that one electron, so you are sending the current through the stack, and then spin up electron and spin down electrons are flowing inside the material as the 2 current model was. So now if you look to the spin up electron goes from here to S and then to transition metal again, but it will just easily walk. There is almost no traffic of d electrons. So you can see here there is no d states available. It's very similar to this normal metal situation, so it will not have so much scattering. It will go to S states here, and there is also no d state, so it will not have scattering due to d states. And then if you go here, there is also no d states available, so electrons doesn't have so much traffic to be worried about. So there will be very low resistance. The situation is also shown here. So for the spin up electron, you have drawn two low resistors here corresponding to each magnetic layer. You do not really need to draw for the normal metal because there will be no effect from the d electrons. So now if you talk about spin down electron, so in the spin down electron, because there is density of state of spin of d electrons are available, it will get scattered. And then the scattering is shown with this dashed line, and then here it will not have so much effect in the normal metal, but this channel is already scattered, so drawn with the dashed line. And if you go again to a ferromagnetic layer, here it will get again scattered. So this channel is scattered from both magnetic layers, so that's why you have drawn two big resistors. So in this way, if you see, spin up electrons have less scattering, spin down electrons have a lot of scattering, but overall the resistance, with this resistor model, you can see that you will have a net flow of spin up electrons and the resistance will be smaller. Now look to the other situation. Now the magnetization of the two magnet layers are opposite to each other. That's why I have drawn also density of states splitted in different ways. So here spin down electrons are moved upward and spin up electrons are moved downward. However, in this situation I have drawn opposite because the magnetization is opposite, and the situation is explained for zero field. Now if you follow the spin up electron, so spin up electron will not have so much scattering here, everything is cold, here not so much scattering, so I have drawn solid line. But if you go into the next magnetic layer, you have a lot of density of state of d electrons available at the Fermi level, so it's going to get scattered. So that's why for first layer I have drawn a smaller resistance, and for the second layer I have drawn a big resistor. So now if you look the spin down electrons, it goes into the first magnetic layer, it has a lot of density of states available from the d electrons and it will get scattered. So, and then there is nothing really happening in the normal metal. You can draw dash line, solid line, doesn't really matter, but the spin down electrons are already scattered. And now if you go further to the next layer, there is not d electrons are not so much available at the Fermi level, so you will not have so much scattering here. So that's why for first magnetic layer I have drawn a big resistor, and for second layer a small resistor. But if you look the two channels for spin up and spin down, in both cases you have almost same resistance situation, so both have big scattering events. In such situation, compared to the previous situation, you will have a larger resistance, which is plotted here. So this gives rise to a change in the resistance if you measure as function of field, which is your GMR effect, and that's how this principle was working. There is a little more to it. You have to also think about spin diffusion length scales, and you have to see the thicknesses of the stack, but moral of the story is that you can literally track the effect from the density of states as well as a spin dependent scattering event. So the take home message here is the spin dependent conductivity is the key ingredient of spin transport here, and two current channel model is actually valid for transition metals. The book, if you want to follow, you can read Coe. It will give you a quite good overview for this one. And if you want to get inspired from more field of Spintronics, you can follow this site. There already 99 different scientists talk working in the field of Spintronics are uploaded, and hundreds talk will be uploaded this month. So if you wanted to see, you can have a look. Thank you very much for the attention.